For me, it's a pleasure to present our study, Failure Detection in Induction Motors using Unsupervised Machine Learning Algorithms. The energy produced by a nation is mainly consumed by four sectors: industrial, commercial, residential, and public. There are machines like fans, pumps, compressors, conveyors in the industry that are based on induction motors. That's why up to 60% of the energy is consumed by them. Unfortunately, the fault only produces inefficiency, and it is detected only when the motor stops working. Thus, early non-invasive detection is necessary to prevent disruption and irreversible damage. Motor faults can be classified according to the constitutive part that is failing. Related to the stator, 38% of cases; to rotor, 10%; to bearing, 40%; and others, 12%. Stator faults are basically shortcuts that can be detected using voltage and current analysis. Rotor faults are discontinuities in the rotors, most of the cases broken bars, and can be detected with current analysis. Bearing faults need to be detected with mechanical vibration analysis that implies an extra effort and cost when compared to the measure of electrical voltage and currents, since this sensor must be next to the motor and must be installed with the corresponding wiring. Also, current analysis is useful only for serious bearing faults. In this study, we propose only current analysis for bearing and rotor faults. The signals are measured in this testbed that includes a new motor mechanical coupled to a DC generator connected to a resistive load. Furthermore, an extra rotor, identical to the original, but with two consecutive bars drilled, is used to emulate broken bars, and an extra bearing, whose auto race has been cut in one side, is also used to emulate serious faulty bearings. The ways of failure detection can be classified in three categories: comparison models, where a simulation of the model is used to compare several variables. Here, it is necessary to know all the specific coefficients and of the machine in order to create a reliable theoretical model. The signal analysis, where voltage and current or other historical data are compared by an expert, and finally, an artificial intelligence model, where learned machine algorithms are trained with faulty and healthy motor data. And here is the question. Remember that there are only healthy motor in file. So, is it possible to create a full model without faulty motor data, ready for implementation in file? In this study, it demonstrated that yes, it is, and we will see how. First, we have to know the difference between a supervised detector and our anomaly detection based on unsupervised learning. Here we have healthy motor data in orange and faulty motor data in blue. Let's see the classic supervised learning algorithm. It is initialized with random values and it is training, and you're having a satisfactory performance. The problem is that the values that rule the model, for example, the weights of the neurons in a neuronal network, can be modified by a can be modified by a human because these parameters doesn't have interpretability. A human cannot modify them. On the other hand, we have the anomaly detection strategy that classifies the data in n clusters and each one has a centroid. Let's suppose we found the position of three centroids using non-supervised learning algorithm. Now it's necessary to enclose the data in order to separate both groups. By the way, these graphics are not real. They are only for didactic purpose. Thus, now we can build circles to enclose it, taking advantage of these centroids. And now the radius should be adjusted. Too small radius will cause orange points to be excluded. Medium-sized radius are the ones, and large radius will include faulty motor data. And now the question is more specific. Is it possible to find these circles without faulty motor data? Well, it needs to be mentioned that we propose a neural network as a baseline, which is a supervised learning algorithm. Non-supervised learning algorithm consists in two options, one based on k-means and one on self-organizing maps. The k-means is not worthed, but the sum shows similar results to the neural network. By the way, the unsupervised algorithms are used only for finding the position of the centroids. They doesn't reach the detection by themselves. Only the anomaly detection based on self-organizing maps is explained in this video. Anyway, the k-means is explained in the paper in case of doubts. These are the constitutive parameters that we need to select. In other words, if we can select them without faulty motor data, a full healthy motor data model is possible. Here we have topology and number of centroids and radius. First, the topology. Let's look to examples of topology. Here we have a linear acentroid topology. And here we have a rectangular 2x4 topology, obviously acentroids. In this study, we evaluated different numbers of clusters for different topologies, and the results are here, in this graphic. The learning capacity is on the y-axis, and the number of clusters is on the x-axis. The topologies analyzed are linear in crosses, square represented with points, rectangular 2 by n represented with asterisks, and rectangular 4 by n with blocks. First, we can see there is no significant difference between the several topologies' performance, but the linear topology presents best elasticity because it decays more slowly than others when the number of clusters increases. Well, we use 600 of data, which means that the general recommendation of n over 10 cluster is reliable for any topology. So, linear topology with n over 10 cluster is a reliable general rule. In this case, we use 68 clusters. And that's it. We have selected the topology and the number of clusters without faulty motor data. Next, and finally, the radius, which is the most critical parameter. First, we have to understand how to set up the radius. Let's suppose we have chosen the number of clusters and we have already found the position of 6 centroids by executing the self-organizing maps algorithm. In this case, we will only analyze the sum algorithm because the results are similar to the neural network. The radius is initially set up with the distribution of the data. In this case, it is the distance between the centroid and the further datum associated with the cluster as is shown in the graphic. But there are some data that is too far from the centroid associated, causing the circles to be too big. This radius is too large. It is necessary to reduce the size of the value. Thus, now we have a value called threshold that allows us to do down to every radius that exceeds the limit value. And finally, we add a value called margin to every radius. In summary, the radius is designed with two parameters, margin and threshold. The sensitivity and the specificity versus these variables is summarized in this graphic. Here we have in the y-axis the margin and in the x-axis the threshold. The curves present the points where the specificity or the sensitivity is constant. Specificity curves obtained based on only healthy data motor and sensitivity curves on only faulty motor data. There are two main zones, the threshold zone on the left where the threshold is effective and some radius are being diminished, and the right zone when the threshold is too large and no radius is changed. The optimal points are in the middle zone, where only the build radius are diminished. The point found with faulty motor is here, in the middle zone, the point A. It is important to understand that the lower specificity we select, the higher sensitivity we obtain. For no sensitivity systems, it is recommendable to use two models, one with 95% specificity, for example, and another with 99% specificity model to classify the results in three: negative, dope, tofu, and positive. However, we can draw the specificity curves with only healthy motor data obviously and set up an arbitrary value. Then select any margin and threshold near the middle zone, and that's it. We can find the model with no faulty motor. See how we obtain sensitivity more than 99% with any specificity equal or less than 99%. Thus, the performance of the model depends almost totally of the failure of the feature selection. The results show that self-organizing maps can reach similar performance to the baseline neural network. K-means show lower performance, and a full healthy motor data sum model can reach 99% of sensitivity and specificity. Finally, the conclusions. The detection of broken bars and faulty bar induction motors with a self-organizing maps-based anomaly detection method and using electrical current analysis is successful. The construction of a fully designed and trained model based exclusively on healthy motor data has two main drawbacks when it is going to be implemented in the file. The first drawback is the choice of the model wavelet, since the performance of the model changes dramatically with the choice of different model wavelets. The second drawback is that faulty motor data are required to tune the threshold and margin parameters. Also, there are some recommendations that could let us select nervy values to get a high sensitivity and specificity without faulty motor data. Now, it's necessary to talk about future studies. First, in this study we used no variable frequency drive, and all the signals were measured in stationary state. The use of BFD must be analyzed in other studies. Second, we have to consider the aging process in file. Fat in gears is reduced, materials like rubber wear out, causing the process to change. A method of continuous learning needs to be studied. Third, we took data in a uniform way in all the power capacity range, from no load to full load. But there are processes in file that limit the correct measurements. For example, crashing machine, short time movement motors, and the way of measure data must be studied for all these different motor behavior. I believe there are two ways to obtain data when the machines permit no optimal condition for measurement. One is to create a way to evaluate it when it's timely to measure, to adapt an automatic data sample collection system, and the other is to modify the process to create a specific moment to measure. Could be while the process is out of service, for example. And that's all. Thank you